All right, guys. So in this second video here, we've been talking about significance tests for population mean. We're going to talk about how to calculate the standardized test statistic and p-value for a test about a population mean. So remember that when the population standard deviation is not known, the best we can do is the standard deviation of our sample to estimate the parameter. However, when we do that, that increases the variability, which is why we have to use the t-distribution. So there are two ways to find the value of the test statistic t. First one is using table B. So here, um, I want to find the specific degrees of freedom from which the formula degrees of freedom n minus 1 and take a look at the table. So for this one, we would have 11 degrees of freedom, which would mean we had a sample size of 12. And if we are looking for um, the upper tail probability here, so once you have your T star critical value, you can look it up on the table. You go to the degrees of freedom and then over to where your particular T value is. Now, the particular T value we had here, let's say was 2.5 or 2.56, 2.57, something like that. That doesn't actually show up on the table, but it lies between these two values, and the probability would be between zero point 0.1 and point 0.2. That's how we would use the table, and then that's how we could make a conclusion for our significance test. But we do have the option to try this on the calculator, so we can use the calculator to calculate p-values from t-distribution. So you can use the tcdf command on your calculator. So once you have the calculator on, hit second variables for the distribution. Scroll down to tcdf. This is the t-distribution cumulative density function. And you're going to put lower, upper, and then the degrees of freedom. In this case, I'm going to use a t value of negative 2.567 and show you how to do that. So I'm going to do the lower tail probability, so negative 1,000, comma, negative 2.567, comma, degrees of freedom. If the sample was 12, the degrees of freedom would be 11. Okay, so if you hit enter there, that's going to give you the specific p-value of 0.013. Okay, so that's how you would do this on the calculator for calculating p-values from a t-distribution. So here's how we calculate the test statistic. If the conditions are met to perform a hypothesis test, calculate the standardized test statistic. T is equal to the sample mean minus the null population mean from your null hypothesis divided by the standard error of the sample. So you find the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis. Again, if it's a greater than, less than, or not equal to, of course, would be a two-sided test. In a t-distribution, and then remember the degrees of freedom are n minus 1. As the pattern has been, the specific formula is not going to be in the AP Stats exam formula sheet. However, it does include the general formula for standardized test statistic, which is the statistic, in this case, X bar, minus the parameter, which would be the hypothesized population mean, divided by the standard error of the statistic, which is sample standard deviation divided by the square root of the sample size. So let's take a peek at an example here. According to the Animal Diversity Web, adult golden hamsters have an average weight of 4 ounces. We've already gone through an example with this setup. They have 30 golden hamsters. They want to test that claim. The mean weight of their sample is 4.033, standard deviations 0.199. They want to test the null where mu equals 4, alternative is not equal to, so it's a two-sided test here. And they define our parameter of interest. So first thing we want to do is explain why the sample result gives some evidence for the alternative hypothesis. All right. And we state that in a sentence. The sample mean X bar is 4.033, which is not equal to 4, which is suggested by the alternative hypothesis. Now, the second question is calculate the standardized test statistic as well as the p-value. So the value of t is calculated as such. A sample mean divided by the hypothesized mean divided by, or subtracted by the hypothesized mean divided by the standard error of the statistic. So it's 0.908. That's our t value. Now, the degrees of freedom are going to be 30 minus 1, which is 29. Okay. And then we can use our calculator to calculate the actual p-value there. So we go second stat, second variables, TCDF, and our lower is 0.908. We would do an upper 1000, and then the column of degrees of freedom, 29. And we get 0.18, but we have to double this because it's a two-tailed test, so multiply that by 2. And we get 0.3713. If you went to the table of values, the t value of 0.908 with 29 degrees of freedom is not going to be directly on the table, but you would get a p-value between 0.15 and 0.20. So if you would double that, it would be between 0.30 and 0.40. Okay, so that's how we get the p-value. So if we want to interpret this, okay, this means if the mean weight in the population of adult golden hamsters is 4 ounces, there is about a 0.3714 probability of getting a sample mean weight of X bar being greater than 4.033 or less than 3.967 ounces by chance alone. Okay. So I'll put it right here for us so that you could see the example answer there. So because the alternative hypothesis is two-sided, we need to consider values of the sample mean at least as surprising as 0.0433 in either direction. So 0.033 above 4, which is 4.033, and 0.033 below 4, which is 3.967. Okay, so this begs the question, what conclusion should the researchers in the example make? Well, here's the thing. Because the p-value of 0.3714 is greater than our significance level, which is 10%, we would fail to reject the null. We do not have convincing evidence that the mean weight in the population of golden hamsters differs from 4 ounces. Okay, so again, as you may have guessed, the calculator can be used to perform a significance test for a mean. So we're going to illustrate this process using the radio station data from earlier in the section. Here we have the data again. And the first thing that we're going to do once we turn on our calculator, clear that off, we're going to enter the data into a list. So stat edit number 1, and we're going to go to list 1. If you highlight L1 and hit clear and then enter, it'll just delete that whole list. Then you can start entering the values 44, 49, 45, 51, 49, 53, 49, 47, 50, 46, 48. Okay, our values are in there. Then we're going to have it do the test for us. So hit stat, then go over to tests, and then we want to perform a t-test, which is the second one. When this screen comes up, we want to pick data. So highlight data and hit enter because we just put it in the in the list there. Okay. So we want to change L1 or the mean to 50. Okay. Because that was the hypothesized mean in this problem, if you remember. We're getting the list from list one. If it was in list two or list three, you would hit second two or um, second three and so forth. But we want to enlist one. Frequency, we're just going to leave it as one. And then we're going to pick mu less than, or yeah, mu less than the hypothesized because we were looking for a one-sided test in the lower direction. Then hit enter or highlight calculate and then hit enter. And there we go. We have the t-test information for mu less than 50. The t-star critical values negative 2.16. The p-value is 0.027. And then we have the sample mean, standard deviation, and sample size. Um, and there you go. If you already have the summary statistics, um, when you enter for the t-test, you go on stats here, and you would directly enter the mean, standard deviation, sample size there. Okay. So, um, again, if you're going to elect to do the full technology method, like we just did here, you're going to get more accurate values than when you use rounding or the t-table. And so we're going to typically use that. But whenever you're performing a full hypothesis test, it's important to do the whole four-step process, even though you can just do all of this on the calculator. So one quick piece of information before we wrap this video up is that the connection between two-sided tests and confidence intervals is even stronger for means than it was for proportions because both inference methods for means use the standard error of X bar in the calculation. So the standardized test statistic uses X bar here and the standard deviation of X bar, as well as constructing the confidence interval. So this allows us to make conclusions about the null hypothesis directly from a confidence interval. So for example, if a 95% confidence interval for mu does not capture the null value, we can reject the null in a two-sided test at the 5% significance level, or otherwise alpha is 0.05. If 95% confidence interval for mu does capture the null value, then we would fail to reject the null in a two-sided test, again, at a 5% confidence level. Now, the same logic is going to apply for other confidence levels, but this again, so like if you did a 90% or a 99%, but again, this is only true in the case of if you're doing a two-sided test. One-sided tests, you can't link the confidence interval to the hypothesis test. All right. Well, that's it for this one, guys. Hope that was helpful to you, and take care.